We can start. So to conclude this week, Misha is going to talk about random partitions at high temperature.
Okay, thank you, Jay. Thank you, everybody, for coming to my talk. If you have any questions, feel free to interrupt me at any point. I'm going to speak about several different topics, but the idea is the same. It's about operators and the moments method in questions that have to do with random partitions and random matrices. Okay, so let's begin with the model, which is perhaps more familiar to all of you, which is the Gaussian unitary ensemble. And I want to say what the approach will be in this particular case, and then we're going to progress from there. So first of all, the title will be, I chose random. Well, it will be about random matrices at the beginning, but really the new part will be about random partitions. And then at high temperature. And I will explain what the temperature is. But for now, let's begin with the Gaussian unitary ensemble, which for me will be, well, first of all, some notation. We have some vector. That's n. The van der Waals determinant will be VA. And the probability measure, that is the GOE, is just something like this. It's proportional to the van der Waals square. And then we have some exponential weights. Now we're going to study this. We're going to study just the spectral property of this ensemble. So we're going to do it perhaps in a different way that you have seen. So we're going to introduce something called the Bessel generating function for a probability measure on n tuples here. So these are real n tuples. So what is the Bessel generating function? Well, first of all, I have to tell you what is the Bessel function. So for me, it will be the following. It will be a function b, which depends on a, but also has some variables x1, x2, xn, okay? I will put here the upper index 1, and I will explain why, because then it will become a parameter theta, which could be any positive real number, but for now it will be 1, that's the simplest case. And by definition, this Bessel function, or multivariate Bessel function, will be some constant, product of k factorials. And then we have the following expression. The determinant of AIXJ, and then you need to divide by the van der Waals, the product of van der Waals of A and the van der Waals of X. Okay, so that's a very simple function. Should be treated as a function on the x's. Okay, and some properties that I will use are the following. So first of all, they're very simple to notice. So first of all, this van der Waals is skew-symmetric on the x-axis. Similarly, this determinant. So when you divide, it becomes symmetric on the x-axis. It's a symmetric function. Second of all, it has certain normalization. So the reason why I chose this factor in front is so that when the x-axis are set equal to 0, you need to take a limit obviously here, because otherwise you don't want to divide by 0. But after that process is completed, this will be equal to 1. So it's normalized so that it's equal to 1 at the origin. And now here's the property that will be important for us, is that this function here is the eigenfunction for certain operators, okay? And there's not just one operator that works. There are many operators. The simplest one that you can see is the following. So it will be an operator which is, I will write it first and then explain it. So we have this van der Waals x, and then I have sum of partial of xj to the k, j from 1 to n, and here you multiply by the van der Waals. So what happens when you apply this operator to this Bessel function? Well, the van der Waals on the x's will cancel out. Then you need to apply this differential operator just on the numerator. right? There will be some AIs coming to the bottom, and then you divide again by this Vandermonde. So this Vandermonde is replaced, okay? So in the end, it will turn out that you get the Bessel function again, but with certain eigenvalue. And the eigenvalue is very easy to compute. It's just this expression right here, the sum of the AJ's to the K. Okay. And here I'm forgetting the upper index one. And this is true for any K, which is a positive integer. Okay. So what's the point with this? Well, I haven't told you the punchline yet. So far, I have just defined this function. This function will be useful because it will be used in the following definition of something called multivariate Bessel function. It's some kind of Fourier transform for probability measures that live on R to the n, okay? And it will be the following. So you consider the definition, if you want to put the following integral. You integrate over the variables a, this Bessel function, over the probability measure, which is the GUE. Okay, so this is a very easy exercise actually, because what happens? So here you have VA squared, and then you need to divide by VA. So there will be a VA in the numerator, right? That's one thing. The second thing is that, okay, this is a determinant. You expand the determinant. There will be a bunch of factors like this appearing in the expansion, and you will have a bunch of factors here. So if you multiply this, you will see that e to the AIXJ minus AI squared over 2 appearing all over here, this expression, okay? So there will be a bunch of factors that are e to the AIXJ minus AI squared over, or minus, yeah, AI squared over 2, right? So you complete this and you will see some factors e to the minus xi squared over 2 appearing all over. Okay, and so the final answer is not surprising that it will be the exponential of x1 squared plus x2 squared plus xn squared divided by 2. Okay, so that's a very simple expression. And what's the point here? Well, you have this probability measure, then you compute this sort of Fourier transform, and turns out that the final expression is very easy. It's just this expression right here. Okay, and that will be useful because we want to apply the method of moments. So in the method of moments, what we will do is to take this operator here, which we know acts nicely on the Bessel function, and then apply it to this equation right here. Okay, and the definition, this is the definition of the multivariate Bessel function of the probability measure, in this case of the GUE. This should be treated as a function of the x's. Okay. So we will apply this operator to both sides of this equation and then see what happens. So on the left side, what will happen is that this operator will go inside the integral. And then when it hits this Bessel function, there will be this eigenvalue appearing, right? So that's what will happen. And on the right side, well, it unfortunately will just be a nasty expression, which is what will give the difficulty of the problem. It will just be this operator applied to this exponential. And whatever it is the answer. Okay? So by doing this application, what I will obtain is the following. So I will have the integral of now this expression right here, aj to the k, j from 1 to n. Then you have again the multivariate Bessel function and the probability measure. Okay. And on the other side, well, you have just the operator applied to this exponential. Okay. The next thing that I want to do, I'm kind of describing you first the proof of something. I will give you the punchline in a second. But the next thing that you will do is to set the xi's equal to 0, so that then we can apply this normalization property here. So once you set the xi equal to 0 in both equations, Now you see what we will obtain. This will be equal to 1. And on the left side, we have the moments of the empirical measures of the GUE. Okay, so that's the punchline. In order to study the moments of the empirical measure of the GUE, you need to study what happens with the application of this operator here on this very explicit function. Okay, so the equation that you really need to study will be the following. Hence, we can put it as a proposition, is that the expectation with respect to the GUE 1 over n to the k over 2 plus 1, sum of ai to the k, I from 1 to n, is equal to 1 over n to the k over 2 plus 1, then the application of this operator, to this very explicit function, okay? And then you need to set the x equal to 0, okay? So that's it. If I want to study the GUE, I might as well study the moments, and I might as well study this expression right here, okay? So as n goes to infinity, you will obtain the moments of the semicircular distribution by using this approach, okay? And this might be more complicated than what you're used to, but the point is that this generalizes for models that have the parameter beta, which is the inverse temperature, which I will speak about now. And then you take the limit as n goes to infinity, and I will mention here that the approach by using these sort of operators in the discrete case was due to Buffetov and Goring first. Their very nice paper in 2015. Okay. So that's something that you're very well familiar with. Maybe not so much the Bessel functions and the operators that appear here, but let's complicate the picture a little more. We're going to use actually different types of operators now. So instead of these operators, which do not have a name, there are some very special operators coming from representation theory that are called the Dunkel operators that I want to talk about next. So next we have the Dunkel operators. Just di will be equal to, this will be my partial with respect to the variable xi, okay? Just for simplicity, I will denote it like this. Then I have a sum over j is different from I, 1 over xi minus xj, then 1 minus sij, and this is the transposition which transposes the variable xi and xj. And this is for all I from 1 to n. Okay? Some very special property of these operators is that they commute. So di dj is equal to dj di. So in particular, this implies that they have a common eigenfunctions, okay? And turns out, yes?
It has a beta parameter.
Well, in this case, the parameter is 1 because I'm just looking at the Gaussian unitary ensemble at the moment. But I will include it in 1 second. Okay. So they have this property of commutativity. And turns out that they also have some similar property here. In fact, you can replace this operator that's circled in purple by the operator which is sum of di raised to the power of k from 1 to n, and you get exactly the same equation. So by applying that operator to the multivariate Bessel function, you get the exact same eigenvalue. Okay. And so you can use these operators instead. Okay. The point is that this can be generalized for general inverse temperature, but also the analysis somehow it's easier, in my opinion. And we also were able to generalize it for the high temperature regime. So again, I'm not talking about one parameter generalization yet, but just as a quick exercise or as a quick example, I hope that this is not too much, but let's try to calculate what happens with d1 square. So this operator, notice that it doesn't look so nice, right? Because it's okay, some partial, but then you have this expression. So if you think about what we actually need to do is to raise that operator to the power of k, so apply k times to some function. So as k starts getting larger and larger, it becomes more and more complicated, this expression. So for example, d1 squared, if you apply to this expression right here, e to the x1 squared plus xn squared divided by 2. And then don't forget that we want to set x equal to 0 to the n at the end. Okay, so what do we obtain? The first application of d1 will be what? Well, it will be partial of x1, that's fine. This actually is very easy because it has this expression, 1 minus transposition. And when you apply that to a symmetric function, that will be 0, right? Because this is symmetric with respect to x1 and any other xj. So the first application of d1 just gives me the derivative with respect to x1, which is x1. So this will be equal to d1. Now you need to apply that to x1 and then e to the same expression. Okay. Now what happens? Then you need to apply it again, partial with respect to x1 to here, right? You need to apply to the first one, then to the second one. That's okay. Now this expression here, what happens? Well, this expression here, in this particular case, it's not so complicated because this will be just this expression. This will be, you need to permute x1 with xj, right? But then you need to divide by x1 minus xj. So that will be also very easy, okay? So this is still manageable. So when k is equal to 2, when you're trying to compute the second moment, that's still manageable. But as k starts to grow and grow, you will see that there will be more of these operators that start becoming non-trivial, okay? And that's where the difficulty appears. But still, you should get the moments of the semicircle distribution. So there's a way that you actually are able to compute all of these limits as n goes to infinity somehow. Okay, let's continue. Okay, actually now we're going to introduce the inverse temperature parameter. So we're going to have something called an inverse temperature. And we're going to see how to generalize all the theory that I have told you and that you're familiar with to this one parameter generalization. So the inverse temperature for me will be the parameter theta. That's related to the beta, which you're more familiar with, as follows. So theta is equal to beta divided by 2. Okay, so when beta is 2, that's the Gaussian unitary ensemble. That will be the same as theta being equal to 1. Okay, so you also have a Dunkel operator in that case. The parameter theta appears here in front of the sum. So theta times that sum, okay? Very easy, actually, at least this operator. This commutativity relation remains the same, okay? Calculation, at least for the second moment, seems to remain the same, but of course it becomes more and more complicated when you have to keep track of this parameter theta. Okay. But turns out that when theta is fixed, you also have convergence to the semicircular distribution by doing the same type of procedure. You need to see what happens when you apply these Dunkel operators to this expression, this exponential, and then you set the variables xi equals to 0. Okay. Now we want to study what happens when theta goes to 0 as n goes to infinity. That's the high temperature regime. So let me just write something here, maybe. Let me remove this calculation. And I will mention here, first of all, I should mention that the parameter theta in the probability measure that we want to look at in this case is the Gaussian beta ensemble, right? Now it will depend on a parameter beta or theta in this case. And it's the one that's proportional to the Vandermonde raised to the power of 2 theta. And you have the same exponential. So I will keep this normalization from 1 to 1. Okay? And you also have that if you integrate, I should probably mention next thing. I'm doing it a little bit disorder, but let's continue. Okay, so for the parameter theta, I should mention that we also have the multivariate Bessel functions. Now we will replace this one by theta, okay? And this will actually be the definition of the multivariate Bessel function. Turns out that by the papers of Dunkel in, let's see which year was this? '89 and '93. So Dunkel in '89 and Obdam in '93, among many other authors who have studied these functions. Turns out that there is a unique function which is symmetric with respect to the xi's, right, on n variables xi, satisfy this normalization property, and satisfy this eigenfunction relation. Now I have to actually use these Dunkel operators. I should mention that there's no obvious way to generalize this operator that was used by Buffetov and Goring for the parameter theta, because this really depends on the determinantal structure that appears when theta is equal to 1, okay? So for general theta, you really need these Dunkel operators of representation theoretic origin. So, and they also satisfy this eigenfunction relation. Sum of the Dunkel operators, a power, where I goes from 1 to n, is equal to this expression, the Bessel function, and this eigenvalue. And this has to be true again for any k bigger than or equal to 1 integer, okay? So those are the multivariate Bessel functions with parameter theta, theta everywhere. Okay? And turns out that actually you can calculate the same integral for general parameter theta as well. So you integrate this Bessel function against the Gaussian beta ensemble, and turns out that the answer is exactly the same. It's actually independent of theta, okay, in this particular case. That's a result of narrating. I mean, it's just an integral. It's not perhaps extremely surprising that you can do it, but you still have to work for it, right? So, I mean, this is a very special case of much more complicated integrals than that narrating has in that paper. Okay. So, and then you can do the same thing. You can obtain the moments of the Gaussian beta ensemble by using this kind of operator approach, okay? And in the first paper, the first result that I will mention, which is relatively new with Benaik George, with Florent, Benaik George, and Vadim Goring, we studied the moments of the Gaussian beta ensemble in this high temperature regime, okay? And we gave a new expression. So I will state the result right here. So we want to study n times theta converges to some constant, okay? So theta will be a constant from 0 to infinity, okay? And then what do we prove? We prove that in this regime, if you look at the moments, of course, the odd moments will cancel, as it's typically the case, right? Because there's this symmetry with respect to the origin. But the even moments have a very special expression. So there are two expressions that I want to mention today. So one is the following. So to calculate this limit of the two-case moment, use sum over perfect matchings. Of 1, 2, 3, up to 2k, okay? Then gamma plus 1 And for each perfect matching, you compute certain statistic of that perfect matching. Okay, I will call roof of pi. I will not go into details of how to calculate this. I will just do an example. So what is a perfect matching, for example? 1, 2, 3, 4, 5, and 6. A perfect matching would pair, for example, 1 and 5, 2 and 6, and 3 and 4. Okay, and what is this statistic counting? This statistic is counting how many roofs have no intersections. So this roof between 1 and 5 has no intersection. This roof between 3 and 4 has no intersection. So the roof statistic of this particular perfect matching is equal to 2. The other roof has one intersection, so that's not counted. Okay, so you calculate these numbers for all possible perfect matches and you compute this quantity. It turns out to be the two-case moment of the limiting object. Okay. And we have another result in that paper also, that there's another alternative expression. It's not easy to see. There's no obvious bijection, but it will be the following. You need to look at Motzkin path without horizontal steps. So Motzkin paths are just going up by 1 or going down by 1. They do not go below the x-axis. So for instance, this is a Motzkin path. Okay. Then you have to give weights to the edges in certain appropriate way.
Motzkin paths without horizontal steps?
Yes.
Tick path.
Oh, okay, tick path. Well, but yeah, that's good. Thank you. Okay, and the weights are as follows. So gamma plus 1, gamma plus 1, gamma plus 2. So the up steps have gamma plus k, depending on where it goes, where it comes from. And the down steps are just weight 1. Okay. So you compute the weight of this, then you look at all such dick paths, right, of length 2k. You add them and turns out that you get the same exact expression. So either way, you compute this quantity here. Okay. Yes.
Does this match the Bouchot-Guillonnet density of states?
I'm sorry.
Does this match the result by Bouchot and Guillonnet of the density?
Exactly. Yeah, yeah. So these are the moments that would compute the explicit density that was given by that paper by Aleix Bouchot-Guillonnet in 2012. But from that explicit formula, even though it's very explicit, it's very difficult to compute much, at least to me, because there is a lot of, it's not as simple as the exponential density, for example. So you're really, even to compute just, I don't know, the second moment, it would be very complicated to me. But yes, indeed. So this is a new result, at least this part. But yeah, some relevant works are this paper, where they compute the density of the measure. And also Dewey and Shirai, 2015. And they have an expression which is equivalent to this one. Okay, so to this second interpretation that I have given you in terms of dick paths. Okay. And I just want to move on to partitions now, but before I just want to say that for random matrices, we have more general results, and this is just a special case. So in our more general results tell us that we have this kind of law of large numbers, as long as these multivariate Bessel functions have nice limits, essentially. Okay, so you can obtain law of large numbers as soon as you know how to integrate your probability measures against these multivariate Bessel functions. Okay, and we give a number of examples there. Okay. Any question about this part? Yes, Jay.
What is the fluctuation for the?
Yes, and we have to do that. But good question. Good question. Yeah, that's the next question.
What is the order for the fluctuation?
We're working on that. We're working on that. We will talk. We can talk later. But yeah, it should be Gaussian. And also, it's nice that I should mention that the world that appears here is somehow a one-parameter deformation, one-parameter interpolation, as a matter of fact, between classical and free probability. Okay, so the classical probability occurs when parameter beta is 0, so when gamma is 0, and the free probability picture will appear when beta is equal to 2, or for any fixed theta, actually. So that will mean when theta is fixed, so gamma goes to infinity, okay? So you will see this kind of interpolation. So if you look at the fluctuations in theory, you will recover, you know, some kind of interesting objects between classical and free probability, but that's still on the works, okay? But it's a very interesting question indeed.
Do your moment formulas still give a valid probability distribution if gamma is negative?
Sometimes. So there is some connection that we found with something called finite free probability. And turns out that if gamma is analytically just, you know, if you look in the sense of formulas and gamma is a negative, I think, integer, you can show by using this finite free probability business that there is some measure with these moments. But from this picture that I'm showing here, we haven't looked at this question directly.
What are the measures for?
They're described in terms of finite free probability. Yeah.
To get tridiagonal stuff.
Speaking of tridiagonal stuff, that's very nice because we will see, hopefully, I have time to reach some of that. So next, I want to talk about more recent work with, I hope I wrote the names of my co-authors, but just in case I didn't, go around. And Vadim Goring. And now we're going to talk about a few works with Maciek Doliega. Well, okay, his name is a little bit difficult to write. And another, well, there's a relevant work also that I will mention with Moll, Alexander Moll. So the discrete picture, instead of looking at eigenvalues of random matrices or at GUE or at G beta E, we will look at partitions. In fact, not necessarily just at partitions, but at signatures. So I'm lying a little bit with this title, but a signature is just a sequence of weakly decreasing integers, okay? Partitions would be if lambda n is bigger than or equal to 0. Okay, so these are called signatures. Okay, and I have to say that there's not an obvious way to kind of say what would be the discrete analog of the Gaussian unitary ensemble or the Gaussian beta ensemble. So there are some competing theories, if you wish, right? For example, some people in this paper with Maciek and Alex, we studied probability measures on partitions for which the sum of the lambdas is fixed, right? So there's something called the Jack-Planck-Harel measure in that case, okay? And then we studied like limit shapes and so on. So that's one possible question. In this talk, I'm going to speak about ensembles where the number of parts, capital N, is fixed, okay? So this is in a way more similar to what I talked so far. So this is work with Maciek Doliega. So we have a paper on the archive and we're working on another one. So what would be the right analog of the Gaussian beta ensemble in this case? I will write the formula and maybe I will say some words about it, but unfortunately I cannot really give a complete explanation for why, because there's no such thing as a canonical way to discretize a probability measure. But this should be the right object. Be some probability measure. Now I will have some parameter here. I'm gonna call it tau. It's equal to e to the minus n tau, tau to the size of lambda. And then I have some expressions here. I have to write some formulas because otherwise you will be wondering what it looks like. Unfortunately, it's not super pretty. Okay, so this part is fine. Here, you need to draw your partition, lambda. This is actually a probability measure on partitions, okay? So in this case, lambda n is bigger than or equal to 0. And so you can draw your partition as a Yann diagram. So you need to look at all the boxes inside your partition. And this is the arm length of the box, this distance. LS is the leg length of that box. A prime is the co-arm length, and L prime is the co-leg length. Okay, so it's not extremely important, but if you wonder, that's how the probability measure will look like. Okay, and we apply essentially the same type of ideas. So we need some analog of multivariate Bessel function. And then we need some analog of the Dunkel operators for general parameter theta. And then we want to apply the method of moments and see what happens. So the analog of the multivariate Bessel functions are called the Jacobi symmetric polynomials. Right, so let's write here, Jacobi polynomials. Now they depend on a parameter theta, on some variables lambda, which are now integers, and x's, which are still real numbers. What is the definition of these objects? Well, they can be defined in essentially an existent type of way as we did before. So by definition, they are the unique functions which are symmetric with respect to the xi's. As for the normalization condition, actually, that's not necessarily important in this theory of Jacobi symmetric polynomials because we can use just ratios of Jacobi polynomials. So really the ratio that we're going to use is this. We're going to use this normalized version of the Jacobi polynomials that you divide by the Jacobi polynomial evaluated at all ones. And there's an explicit expression which tells me that this is non-zero. Okay, so this is so that when evaluated at all x is equal to 1, you get 1. Okay, and I need to give you an expression for the operators that diagonalize these Jacobi polynomials. They are called the Cherednik operators. Okay. Instead of the Dunkel operators, I have the Cherednik operators. They are the following expression. So you have chi I, it will be xi partial with respect to xi minus theta I minus 1 plus theta. I just want you to see a little bit of, how much more difficult this object is. It looks the same. However, just the difficulty of this expression makes it much less amenable to analysis. It's not only that it looks very difficult, but I will explain here what the difficulty is. But okay, once we have this definition of the Cherednik operators, then the Jacobi polynomials should satisfy the following property, which defines them. You take, again, the powers of the Cherednik operators, you add them, and then if you apply to the Jacobi polynomial, you should obtain some eigenvalue. And the eigenvalue that you obtain is the following. So it's some shifted version of the parameters lambda. Okay? So it's not just lambda I to the k, but it's lambda I minus theta times I minus 1. Okay, and so these properties uniquely determine these Jacobi polynomials as polynomials of, which have all sorts of nice properties. They are homogeneous, they're orthogonal with respect to some inner product, and so on. Okay. Very good. How did I call my probability measure? Okay. So then using these Jacobi polynomials, we define something called the Jacobi generating function. There's another definition due to J. Huang over there, but he has symmetric functions, whereas here we will have symmetric polynomials. Generating function. So it will be the following. So you take this normalized version of the Jacobi symmetric polynomial, and then you integrate it, well, in this case, you sum it up against this discrete version of the Gaussian beta ensemble with this parameter tau. Okay? Again, imagine that this is a very complicated integral. Well, in this case, it's a very complicated sum, but here is one of the reasons why this is a very special probability measure. One can compute this sort of discrete Fourier transform very explicitly. And the answer is just the exponential of tau, and then you sum from 1 to n xi minus 1. For those who are experts, this is a particular case of a Jacobi measure, okay? So for general Jacobi measures, where one of the two specializations is the alpha specialization, one can calculate completely this Jacobi generating function, okay? So in this particular case, it's giving me this expression. Okay, and now I'm in perfect position to apply just the method of moments. Namely, I will take these Cherednik operators. I will take this operator right here. And I will apply it to this equation, right? So when you apply it here, you will obtain the moments of the corresponding empirical measure. They will be in terms of these shifted coordinates of the lambdas. That will be the left side. Okay, you need to set x equals to 1 after you apply the operators. And on the right side, well, I will obtain something which is exactly what I need to compute, the limit of, right? If I want to compute maybe in the fixed temperature regime or in the high temperature regime, that's up to me. But that's the idea, okay?
Right.
Yes.
To understand why before you got x squared and now you just get x.
Xi, yeah. Yes, so this equation is right, but yeah, you're right that before we obtain x squared, and now
So there is no way to connect.
No, then there is, like you would need to set xi equals to, I forget exactly, but then there is some limit transition. Maybe you need to, yes.
It's a generated function Poisson distribution. Poisson distribution has normal limit. That's how you connect.
Right. Yeah, you need to do this same transformation before the limit, but I forget exactly what it is. Okay. So now I'm just in perfect position to apply it, but the difficulty, okay, even though the operators seem the same, there's a critical technical difficulty here, which is that now the operators chi-i's depend very non-trivially on the index I. So how does that look like? Well, okay, these two sums, first of all, are kind of annoying that it's not just one sum, but you have two sums here. But this term really is the difficulty here, minus theta times I. Before we used heavily the following expression. So we would love if you apply the operator chi-i to any expression, let's say to this expression right here. And then you set x equals to 1 to the n. And you will obtain the same as if you apply a different Cherednik operator to this function. And then you set the variables x 1 to the n. Okay? But that's not the case here. Okay, exactly because of this part, among other things, but specifically this part. So here we have to kind of go around this.
Sorry, and this part is also even present for theta equals 1, right?
For theta equals 1, yes. So you know, here it's not clear how to do it. Actually, for theta is equal to 1, then you have to go back to the work of Buffetov and Goring, where they do this other thing. So yeah, so. Well, for theta equals to 1, of course, there's many other ideas that you can use. But if you want to do even for fixed theta, in this discrete case, we don't know how to do it because there's this difficulty, which is there's not equal to. So given what I want to tell you, which is kind of very interesting, at least I want to state the results because in my opinion, they look pretty, even though they're kind of long. I'm not going to discuss in a lot of detail how to resolve this question. I will just mention that there is a new idea in our paper, which is to use the Hecker relations. So this is it's just a trick really, but it's a trick that kind of hopefully can be used further in this type of theory. So the Hecker relations tell me that you have the following equalities. So I'll just write it here. I minus theta times the identity. Okay, it's this kind of relation right here. And okay, it seems kind of very, oh, I forgot, sorry. Chi I minus 1. It's algebraic equation, right? The Cherenkov operators form some kind of algebra, and you have this equation inside that algebra, okay? So in particular, okay, you can consider the representation on these symmetric polynomials, and then this is just an equality in terms of operators. So what we do here is somehow use this equation to express what we want this part in terms of chi I minus 1, okay? So really what we want is how to apply this type of operator to the Jacobi symmetric function. So what we do is to lower the degree of the chi I by using these Hecker relations. And in reality, at the end, it will turn out that we only want these expressions right here. So we'll reduce it to just the case when I is equal to 1. And we want to study the limits of these objects. So the first idea is to reduce it to this expression right here. And then when I is equal to 1, actually a miracle happens, which is that, well, maybe not a miracle, but it's kind of nice that I minus 1 is 0. So this, when I is equal to 1, cancels. And when I is equal to 1, this sum disappears. So really, you have something which is exactly almost the same as the Dunkel operator. So then we just use the same analysis that we did with Florent and Vadim, and we solve the problem. So we're able to solve the problem, and I will tell you what the answer looks like. And here the answer is much more complicated. So, of course, because we employed like a lot of power, not only just a lot of calculations, but really like all of these ideas. So this is in our preprint, which is already on the archive. And it tells me that the limit, the moments, in the high temperature regime, we consider the high temperature regime. Actually, I should mention that the fixed temperature regime, at least certain questions were studied by Juan. We also recover those results in our paper. There's an appendix in our paper, okay? But here is the new part of the results. So you look at the moments. What is the answer? So now it will be a sum over now genuine Motzkin paths, okay, not dick paths. So they can have horizontal steps. Of length k. And then you need to calculate some weight of that Motzkin path. And then you need to divide by 1 plus the number of horizontal steps at height 0. So for example, if we have a Motzkin path of length 8, in this particular example. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8. And your Mothkin path is like this. Horizontal, up, up, down, down. I will tell you what the weight is. Well, you put weights on each edge. So it will be here gamma, 1 plus gamma. You can kind of figure out, maybe this is a nice exercise for you to figure out what's the rule. I think the up steps are gammas. The horizontal steps at height 0 are gammas. And then the horizontal steps will depend on the height, right? So if it has higher height, it will become 1 plus gamma, 2 plus gamma, and so on. The down steps are also depend on the height. So 2 plus gamma, 1 plus gamma. Okay, so the weight of gamma will be the multiplication of all these edge weights. The number of horizontal steps at height 0 in this case is 1 for this particular example. Okay. And I should mention that this is in the case when tau is equal to gamma. I chose the simplest case. If tau is not equal to gamma, it will be something similar, but there will be a sum inside. So it's a double sum. Okay, it's a little bit more complicated expression, but it simplifies in this particular case. Okay. That's nice because we can now say that the limiting object is the unique probability measure which has kth moment given by these expressions right here. Okay, so it's some kind of formula, but then of course, we would like to find the density of this probability measure similar to this.
It doesn't have to be even in this case.
No. Here k doesn't have to be even.
The measure would be positively supported, right?
Yeah. So here k doesn't have to be even. So because it's a probability measure on partitions, so now actually it's on the other side. Well, because you subtract theta I minus 1, actually the smallest particle is lambda n minus theta n, so that's roughly speaking minus gamma. Right? So it's a little bit negative, but not completely negative. Okay, so that's our result, but then of course you want to recover the measure exactly. How do you compute the measure from these moments? It's complicated, but luckily we have another result. And actually this is very, very interesting, in my opinion. Another theorem, which tells us that if you combine these moments into the moment generating function, I will tell you what the moment generating function is. So there's another expression. Okay, so in theory, it's just this z to the k over k factorial, and you sum all of that. But turns out that you actually can express it in terms of this so-called confluent hypergeometric function. Okay, so here you have gamma z minus gamma. This is equal to exponential of gamma. Then you have some operator that I'm going to call L tilde. The moment generating function of my limiting object, which depends only on this gamma, minus x. I should mention that this is, again, when tau is equal to gamma, minus e to the gamma x minus 1 over gamma x. I will explain what this means in a second. That's the formula. What is this L tilde? Notice that this is a function of x. So this L tilde of this function of x is equal to this other function of z. Okay, so this is really a function of z, right? You can think of it formally. So this is a formal power series in z to the minus 1. then you take the exponential. That will be another formal power series in Z inverse. This will, you can expand it also. It's a formal power series in Z inverse. This is an equality. And okay, looks very complicated, but
What is MU?
this is the moment generating function of the limiting object. Thank you for the question. And here, mu gamma is the unique probability measure which has these moments. Okay. So this, I should mention, this is we call the formal Laplace transform, okay? Because in theory, this is like the Laplace transform, but really, like, you would have to make sense of, okay, this is a function which you can take the Laplace transform of. So we really just put this as an equality of formal power series. And what's the good thing is that, okay, you take this, then you take the logarithm, you take the inverse Laplace transform, and then you will obtain this characteristic function of the probability measure. And in theory, you can recover the probability measure. So we have done it, actually. We know a formula that's in preparation. So I will just finish by showing you a picture of what this looks like. Before I hide this, well, okay, I'll put it back. So hopefully nothing bad happens. Right, so what's this picture? Maybe I should have said right before putting this, but the probability measure that I'm looking at, I told you that it is a discrete version of the Gaussian beta ensemble, right? So how can you understand it? You can understand this from a different point of view, but for example, one point of view is that there is something called the Dyson-Brownian motion, which are just non-intersecting paths. You can think about Dyson-Brownian motion as non-intersecting paths. And if you look at fixed time distribution, that's the Gaussian beta ensemble. Goring and Shkolnikov, I'll mention just here, among other things, in their paper of 2015, already 10 years ago, constructed a discrete version of this Dyson-Brownian motion. Okay, and that's exactly what's pictured here. Okay, so these are some discrete version of the Gaussian-Brownian motion, and the fixed time distribution, time is in the vertical side, are exactly given by this probability measure that I'm studying the limits of. Okay, so you can see here, this is a picture that looks like the Dyson-Brownian motion. This is when theta is 1, so this is fixed temperature, and this is what you would expect to see if you have seen the picture of the Dyson-Brownian motion at some point before. Okay, this is just a discrete version, but it looks exactly the same, or more or less the same. Yes.
C'était quoi? C'était terminateur?
Yes, I think so. Yeah. The second one is when theta is already very small, but theta times n is fixed, is 120. Okay, and you will see that there's some different phenomena. It doesn't look at all like the first picture, and the next one will be also when theta is small. It's just, you know, theta changes, of course the picture changes, but these two pictures have the same character. And if you look closely, let's say at the second picture, what you will see is that I want to find what's the fixed time distribution. So you need to look at the horizontal slide and see what happens there. So what will happen if you look at the horizontal slide is that there will be these small intervals, right? The measure will be uniform on these small intervals, and I'm able to tell you exactly what are the limits of these intervals in terms of the spectra of certain Jacobi operators, okay? That's our result, which is in preparation. And that completes our quest for this part so far. It's very, so is there any question before I put this back on?
So,
Back up?
so on that right picture, do these eigenvalues exactly coincide? I mean, do these lambdas exactly coincide or not? No, they have the theta shifts, right?
Yes, yes, they have the theta shift.
Oh, and theta is very small.
That's why there is something non-trivial.
Right, and then theta is very small, that's why they're almost coinciding.
Exactly, exactly. Yeah, exactly. So they are almost coinciding, but they do not exactly coincide because of the theta shift. So that's something that doesn't happen in the continuous case. The discrete case has this phenomenon.
In the limit, they still coincide, right?
No, in the limit. Well, if you know next to each other, yes, but let me see. So how do I stop share? Okay, so I think I already have abused too much of your time. Thank you for listening to me. And if you have any questions.
So I have a question about the symmetrized Cheredek operators that you are using here. I was wondering if they have a nice action on the other basis of the space of symmetric polynomials, like floor sums, for example.
We didn't take a look at that. So we really only used them quite directly, only those, and we didn't take a look at any possible differentiation. Vadim also suggested some different operators. He has a recent paper with Dunkel, I think, about different types of operators which satisfy this property, which have the Jack symmetric functions as eigenfunctions. And okay, so there is many possibilities to take a look at, but we didn't.
Do you know how tractable the McDonald case would be? Like, or is it just too complicated?
Well, we didn't take a look at that because, you know, really the random matrix thing, you know, is at this level, right? This is the random matrix in McDonald's. Okay, then you need some different interpretation maybe of your phenomenon in terms of random polymers or something like that. I don't know. We didn't take a look, but there is some recent work of Forrester also, which might be related, where he looks at some kind of Q versions of Gaussian beta ensembles. So I will just mention those papers.
Let's thank.
Okay.